that this time it will be okay, no problem. I'm not sure what happened last week. The recording was not saved, but I hope this time it's okay. So acid-base equilibrium, and then the equilibrium that includes the acid and base, right? Acid and base reactions as well. So we know that acid and base react and then produces water and salt, right? So I'm going to ask a question that since they're producing water and salt, why they will have to produce an equilibrium? That would be a good question, and then we're going to ask, we will see why they will produce an equilibrium even though they produce some product. So our learning objectives for this lecture is ionization constant of water. First of all, we will learn ionization of constant for water so that it will be much more easier for us to know the ionization constant for other thing other than water, like any other acid or base or anything. And from that constant, how do we use that constant to understand the pH of a solution? pH is the measurement of acidity, right? So measurement of acidity based on a pH scale, that is from 0 till 14. So to calculate that, to put into number the acidity, the pH, acid or alkalinity of the solution. So the pH, we need to know the Kw or ionization constant of that solution. And with that pH, we will start to calculate the hydronium ion and hydroxyl ion. And this hydronium ion actually that is involved directly related to pH. It is indirectly also related to pH. We will see that because there are pH and POH. So it is pH and this is related to POH. So both are important actually. We will see. Acidity constant from those equation, and at the end all these things we are learning to understand better the buffer solution. We have, I think we talked about it before, the buffer solution. So what is the buffer solution, how do we prepare it, and what is it is, why it is important to know about buffer, or what does it do, the buffer solution. We will be learning it. To understand, before we go more into this acid-base equilibrium, revisit or refresh our memories about Bronsted-Lowry, acid and base definition. There are many other definitions that we put, at least 3. And out of that, we studied Bronsted and Lowry's acid and base definition. That all is quite easy. All includes the proton, right? If it donates proton, if it's rich and donates proton, then it is acid. If it is not rich and accepts proton, that is a base, right? So this is quite easy to remember, Bronsted and Lowry. So Bronsted says that any substance that donates proton, it is an acid. All right. So water, whether water is an acid or base, depends. Water is very smart. Water is amphoteric, which is, it depends on the situation. If it is with a strong acid, then it will become as base. If it is a strong base, it will behave like a acid. So it is, that's why it is called amphoteric solution, substance. And before we go more into this ionization constant and equilibrium thing, just to put some perspective about the acid or bases that we will be using in our daily life, or some of them we will be learning here as well, that how do we use it for our daily life. Sodium iodide added to iodized salt, all right, and sodium chloride, who doesn't know, right? Sodium chloride is a table salt. Everybody eats it. We have taken it in the morning as well. So potassium iodide is the iodine salt, right? Some of the salt on the packet is written is iodine, iodized salt, table salt, iodine, that is is good for this pituitary or what's there is a gland here for that, and it's good for that. Deficiency would make that gland too bigger or something like that. Sodium fluoride, so potassium iodide, it is a salt. Sodium fluoride is a salt as well, and this is added to toothpaste. We also use this morning as well. All right, and interesting thing. Okay, another thing I'll go later on. Sodium bicarbonate is a baking soda that used for mainly for frying or baking or something like that. So the baking soda that is used makes the food tastier. Sodium carbonate is a cleaning agent. Sodium sulfite, preservative. Sodium hypochlorite is bleach. Drain cleaner, antacid, magnesium hydroxide, aluminum hydroxide. This hopefully you don't need to take, but sometimes we need to take, because if it is too much acidic food or we have a reflux, we need to take this thing. Now, can you see the contrast between them? Sodium chloride and hypochlorite. See the contrast? We just need to add one oxygen atom there to make it a poison for human. I mean, if anybody drinks the bleach, he or she not going to survive, right? Whereas sodium chloride, every day we take, to some extent, of course. Excess in everything is bad, but to some extent we. Sodium carbonate, sodium bicarbonate. Sodium bicarbonate makes the food tastier or crispy, or maybe something like that. And then sodium carbonate is the cleaning agent. We cannot survive taking the sodium carbonate itself, right? Just one hydrogen. Sodium sulfite and sodium sulfate. Sodium sulfate is the preservative. Sodium sulfate is not. Sodium sulfate is quite strong to our health. I mean, it's not good. Sodium sulfate, SO4. So just one more oxygen. It is not for one more oxygen or one more hydrogen or for chlorine. It is the nature of that compound that will be used, and it has to do something with their structure. So probably I just put this slide for you to understand or think that how and why just one atom of something else is cleaning, I mean, producing it from food to poison, right? So if you are interested, okay, if you're interested to know more about chemistry, probably you will learn about it, no? Right, now we move into the ionization constant of water. So water, why, first of all, why I am saying that ionization constant, whether it's water, acid or base, right? So why should water go for ionization in the first place? Well, water itself, when we look at the water, the bottle or the lake, the sea or wherever, sea is different, sea there are a lot of salts, but lakes or our water bottle or whatever, the water actually is going for self-ionization. And the water that we know, H2O, much of it is actually H3O and OH plus, negative hydroxyl ion in that water bottle. It depends on what degree the ionization happens. But if even nothing there, still water will go for self-ionization. How much does it do, self-ionization? So since it is a self-ionization and then it is a very weak, a very small amount, self-ionization will happen normally. So there is a double arrow between them or both way arrow between them, which tells us that there is a reversible reaction. Once there is a since this is a reversible reaction, there's supposed to be an equilibrium between them, right? We have seen it before. And since there is an equilibrium at some point, we can express it as an equilibrium constant by taking the K, that is the equilibrium constant, and why I put R. So RF, the forward reaction, RB is the backward reaction. And then since the equilibrium, so we put this product over reactant concentration. Of course, it is in concentration, not in number of moles. But since this is L, that means liquid, and it is not much, it does not dissociate a lot. So we can just consider it is not there because it is liquid, right? We only consider gas or aqueous medium. Liquid and solid we do not consider. So hydrogen, water and water, it will not be considered here. So Kw rendered to be just equal to the concentration multiplication of the concentration of hydronium ion and hydroxyl ion. And interesting thing is, at certain temperature, hydronium ion and hydroxyl ion will be the same, exact same amount. If it is X amount, it will be X amount, because this hydronium ion is produced from breaking down this water, right? Or dissociating this water, ionizing the water. So hydronium ion produced, so to produce one hydronium ion, one hydroxyl ion will be a byproduct. In that way, we can say. So we cannot produce hydronium ion and say that, no, I don't want to produce hydroxyl ion. No, it doesn't happen that way. It will automatically come along. So that is why if I produce X, it will be X amount. If there is Y amount of hydronium ion, there will be Y amount of hydroxyl ion. If it is Z amount of hydroxyl ion, hydronium ion, it will be Z amount of hydroxyl ion as well. So whatever is this, so it's the exact same amount, and that is why we can just take squared and remove the other one value. Or you can take the other one squared and remove the hydroxyl value as well. All right. So this is it. And then the concentration of water is about 55.5. How do we know that? The concentration of water? How can we find the concentration of water? Or can we make it more concentrated or less concentrated? Like 1 liter of water at normal temperature and pressure, it will have 1000 gram, right? 1000 gram. And what is the molar mass of water? 18, right? 18 gram per mole. So if we divide by gram over mole, then we will find 55.55 or about 50.56 or 56, about 56 mole. I just rounded off. I just rounded off the values. So yeah, it is 55.56. So this is the number of moles of water. And then it was conducted an experiment and found that at 25 degrees centigrade, it is important, at 25 degrees centigrade, the water, this water will dissociate, and then it will have 10 power negative 7 molar of hydroxyl ion, 1 times 10 power negative 7 actually. And since hydroxyl ion and hydronium ion is the same amount that will be produced, so there will be 1.7 times both. And that is why we can square it and find 1 times 10 negative 14. So this is universal constant for this, the Kw for water at 25 degrees centigrade. All right, at 25, and it depends on the temperature. Because we have seen that equilibrium can be shifted with the help of temperature or concentration. But the thing is, how can we make more concentrated water? If we boil the water up, what will happen? Boil the water down, what will happen? It will become 500 milliliter, right? But still the same thing, 500 milliliter water, there is nothing else, only water. Or if we add another 1 liter of water, it will become 2 liter water. So it's still the same thing, right? So that is why, I mean, we cannot make the water concentration change, but only the Kw value will change according to the temperature. Since the equilibrium shifts with the help of temperature. Okay, so acidic, basic, and neutral solution. When their hydroxyl ion and hydronium ion is equal, we call it a neutral solution. Neutral solution means acidity and basicity both are same at that temperature for that solution because both are balanced, checked. But if hydronium ion increases, right? If hydronium ion increases, then what will happen is hydronium ion increases, the balance is not there anymore. It is not 50-50. It is something is 60 or is 40. So hydronium ion, because it's positively charged, so it is acidic. It produces acidity, and then the acidity will increase, or acidic, so it will become more acidic. And opposite is true as well. When hydroxyl ion is increasing, then hydronium ion, it becomes more basic or alkaline solution. Okay, so this is the rule. And then you can ask that just now you say it will always be the same, so why it will increase or decrease? That would be a good question if anybody asks, but since nobody asked, I ask myself and then I'm answering it, that if I add hydroxyl ion or hydronium ion to the solution, let's say the solution had nothing else, just 50-50 or equal amount, then suddenly I add some hydronium ion to the water, then of course it will increase, or hydroxyl ion to the water, then it will increase the hydroxyl ion. And that is how they become hydroxyl ion, acidic or basic solution. pH, what is the pH? Since we know that concentration of hydroxyl and hydronium ion, so pH is the negative logarithmic value of the hydronium ion. All right, pH is the negative logarithmic value of hydronium ion. So if we can find the hydroxyl ion or hydronium ion value and take the negative log of that value, right, so that it will become, we can find the acidity of that solution. Okay, we can find it is the acidity of the solution. Okay, so all right, and now if we rearrange this solution, rearrange this equation, we will see that hydronium ion pH we can find. So if we have the value in our hand with us, the concentration of hydronium ion or hydronium ion, one thing just to make sure is be informed that hydronium ion, it is the perfect way of writing. Actually, the water is actually in this form, in the water, hydronium ion and hydroxyl ion, but it takes time to write and also to call it hydronium ion. So sometimes we will just mention by hydrogen ion or proton. We just call it proton or hydrogen ion, right? So this is interchangeable. This is more perfect way of calling it. It is less perfect way, but it is to save time, to make it more convenient, we just call it hydrogen ion. All right. So if we have the concentration, if we know the concentration of hydronium ion or hydrogen ion, we can find the pH of the solution. pH of the solution. And now, if we know the pH of the solution, right? Alternatively, if we know the pH of the solution, we can find the hydrogen ion concentration in that solution. What will be the hydrogen ion concentration in the solution, or how many how many moles of hydrogen ion in the solution, we can also find in that way, right? Another important thing that pH scale that I mentioned is from 0 to 14, right? Within this, the value should be within this, the pH scale. If somebody said that the pH is 15 or pH is -1, it is not correct. It is not correct because mathematically pH scale should be 0 to 14. And pH and pOH both together makes it 14. So 0 till 7, actually less than 7, let's say 6.9, it is acidic scale, and 7.1 until 14 is a basic scale or alkaline solution. Okay, so 0 to 6.9 more. So 7 is the neutral. But when we go from 0 towards 7, we understand that the solution is getting more towards neutral. At 7, it is neutral. Generally, at normal condition, normal temperature, normal pressure, at 7, it is neutral, right? But it can, the neutrality of the solution can depend on the time, on the condition. At higher temperature, higher pressure, the neutrality is not always 7. It is in the between. That is the thing, that it is in the between, that is neutral. All right. So we'll see why I'm saying that it can change. But we understand that 0 to 14, the pH scale. So from 0 towards 7, it is acidic. It is getting towards neutral. But 7 towards 14, it is basic, getting towards basic or alkaline, from neutral to alkaline. And 7 is the perfect neutral at normal temperature condition. So the pH plus pOH is equal to 14, right? And from this equation, we also can find many things, that if we know pH of the solution, we can find the pOH of the solution as well, right? Just 14 minus pH should be the pOH, isn't it? Or vice versa, that way, just arithmetic way. And now this is the everyday thing that we use. The ACL in the lab that we use is around 1 or less than 1.1 maybe. And the lemon juice that we eat for our tea, iced lemon tea or whatever, it is pH 2, apple cider vinegar, all these things. And then it gets towards the higher pH all the way with baking soda, then hand wash, hand soap, a lot we are using at days, eggs. Some veggies will be alkaline solution mostly. So all these things actually, it depends on what type of product we are, but it is in between our 0 to 14 scale. From this different color, we do not mean anything, just to differentiate that pH 1 to 2 to 2 to 3, 3 to 4, 4 to 5 is a difference. So different color has been given. There is nothing related with the pH or color with this. Different thing can be same pH, or different color can be different pH as well. Now, example 1. Let's go and see that. Calculate the pH of the following solution at 25 degrees centigrade. All right. At 25 degrees centigrade, the pH of the following solution. Wow. What will be the pure water solution? pH. What is the pH of pure water at 25 degrees? 0.02 molar HCl, 0.3 molar barium hydroxide. What will be the pH of the solution? We understand that is a neutral, is strong acid. It's acid, we know, is strong base. But what is the pH of the solution? And Kw is given that 1 times 10 negative 14 at 25 degrees centigrade. So water that we have seen, it dissociates partially, and then it produces hydronium ion and hydroxyl ion, and hydronium ion and hydroxyl ion is equal, right? It is equal unless you put anything else. If there is only water, nothing else, then there is hydroxyl ion and hydronium ion should be same, equal amount. So Kw value is equal to, I mean, from there we see that concentration of hydronium ion times the concentration of hydroxyl ion divided by this concentration of water and this water. But these two water are liquid form, right? These two are liquid form. So since they are liquid form, we do not take it here, we do not consider. And that is why it becomes Kw is equal to hydronium ion times hydroxyl ion. Hydronium ion and hydroxyl ion, it is same, so it is squared, and from that value we find the hydroxyl ion just inverse, so root over Kw value is given, it is here. So we find the hydroxyl ion, hydronium ion value is 1 times 10 negative 7, right? So pH is negative log of that value, of this value, 10 negative 7th pH. pH is the negative logarithm of that value. And this is how we find the pH is 7. So this is a proof that we have at 25 degrees centigrade, pH is 7, the neutral pH is 7. And that is why it is neutral. Now it is a strong acid, and the acid is 0.02 mole. I think we remember that to find the K value or equilibrium constant, we need to know the equilibrium concentration, right? We need to know the equilibrium concentration of that. But for this acid is strong. Acid is strong acid. So what will happen is fully it will dissociate. There will be nothing left. There is no double arrow here or reversible. It is not a reversible reaction. It's just dissociate fully, and there is no leftover. There is no leftover at final time, at final stage. 0 molar HCl left. We started with 0.02. All 0.02 will be dissociated. So how much of hydronium ion is produced? It is the same, right? Since all of it has been dissociated, so hydronium ion full of this 0.02 molar of hydronium ion is being produced. So hydronium ion is same, and then we can find the pH is negative log of this value. So we can just put this value here, take the negative 10 base log, and then it will be 1.7. Barium hydroxide, however, it is the stoichiometric ratio is 1:2, so barium is 1 and hydroxyl ion is 2, right? Hydroxyl ion is 2. For 1 mole of barium hydroxide, 2 moles of hydroxyl ion will be produced. Okay, so from there, hydroxyl ion concentration. How do we know the hydroxyl ion concentration? Because it is given that 0.3 molar of barium hydroxide. Right, 0.2 molar, 3 molar of hydrogen peroxide. So from here we have to produce the pH, right? pH, and this is negative log of hydroxyl ion, hydronium ion, sorry, or hydrogen ion, negative log of hydrogen ion. Hydrogen ion, there is no hydrogen ion here. This is barium hydroxide, this is barium, and this is hydroxyl ion. There, where is hydroxyl ion? I mean hydronium ion. H plus or H3O plus, no. But we can find it from here. Hydronium ion is equal to, because Kw is equal to hydronium ion times hydroxyl ion. So from that relation, we can find this way. Just now, we have to find out what is the concentration of hydroxyl ion. What is the concentration of hydroxyl ion? Barium hydroxide is strong base as well. sodium hydroxide, potassium hydroxide, barium hydroxide, they're strong base, so they will dissociate fully as well. All right, they will also dissociate fully. And then, since 0.3 moles of barium hydroxide, 0.3 molar, 1 molar produces 2, so 0.3 will produce 0.6 or 0.3 times 2. Right, 0.3 times 2, we put the values here, and Kw is already given. So from that, this is the hydronium ion concentration is 1.6 times 10 negative 14. This is the hydronium ion concentration we found. And we can just put the value in the negative log. pH is negative log of hydrogen ion concentration, right? So hydrogen ion concentration. So we just plug in this value here, and then we find the pH from there. All right. So this is how we can find. There is another way we can do it. Oh, okay. There is another way we can do it. We can consider hydroxyl ion as it is, because pH plus POH is equal to 14. Right? So POH we can find by having the concentration of hydroxyl ion as it is. So 0.06 molar of hydrogen, hydroxyl ion. We put this value here, and then we find the POH is 1.22, and POH, if 1.22, just negative 1.22, we will find the hydrogen pH of the solution. And now, how pH is affected by temperature, right? Kw value, like any other equilibrium constant, depends on the temperature. And then from this table, we can see at 0 degrees centigrade, the water has a pH of pure water is 7.47. All right, 7.47 pH at 0 degrees. At 0 degree. At 5 degrees, 7.37, and 25 degrees, 7. So this is because water is an endothermic reaction. It needs heat to be dissociated. So if we heat the water, boil the water for whatever purpose, you boil the water for coffee, for tea, for whatever, you are putting heat, right? And then the water becomes more dissociated. That is another way for dissociating. That is why when the water is hot, many things get dissolved in the water easily. Of course, heat is one thing. The ionic character of the water is another thing, that it is dissociating many things. Dissolved. Okay, that is different thing. Okay, so at 25 degrees centigrade, 7, the pH of the water is 7. And this is the normal or neutral pH of the water, or the water we call pH, and neutral at 7, right? And all of us want to see, or whenever we buy water, I don't know whether you see, we see that the pH, what is the pH is given on the label. If it is 6.5 pH, I don't think you will buy at 25 degree, right? Or if it is 7.5 at 25 degree, I don't think you will buy the water. But 7.4, yeah, it's good. Most of the water you will see is 7, 7.3, 7.2, 7.4, something like that. There is one reason for that. We'll see at the end of this lecture. Okay, so at 25 degree, the water has 7. That is the normal pH. But when we increase the temperature, more water dissociate. More hydronium ion and hydroxyl ion produced. So water becomes more dissociated, more polar, right? More ions produces, and that is why the pH decreases, because no matter what, if we increase more hydroxyl ion, the pH will decrease, right? The pH will decrease if I have more hydroxyl ion, hydronium ion in the water. So since it is increasing, hydronium ion is decreasing, and then at 55 degrees centigrade, the pH of the water is 6.57. At 100 degrees, 6.15, the pH. But this pH at this temperature is the neutral, because at this temperature, for this pH, if the water has this pH, then it will have equal amount of hydronium ion and hydroxyl ion, right? Okay, so it's the new normal. At that temperature, it is a new normal. The water is, the pH is getting made higher or lower, it doesn't matter, but water is still have the equal amount of hydronium ion and hydroxyl ion, equal amount. And that is why the water is still neutral. Okay. Example 2, calculate the concentration of hydrogen ion and hydroxide ions in blood if the pH of blood is 7.4. Given the Kw value is 2.5 times 10⁻14 at 37 degrees centigrade. Okay, so this is another reason that your the water that we buy is about 7.4, 7.35, 7.4, not more than that. Okay, 7.2, around that, because our blood pH is 7.4. And our blood is the buffer, we'll see later on. So the problem is asking us to calculate the concentration of hydrogen ion and hydroxide ions in blood if the pH of the blood is 7.4, given the Kw value is this. This is the Kw value at 37 degrees centigrade. All right. We know the pH of the blood, so that we can find the hydrogen ion concentration very easy. Just the anti-log of this the pH, right? So hydronium ion is 10 power negative pH is the anti-log of that value. So we can just put the value here, 7.4, negative 7.4. Instead, we remove the pH and put 7.4. Then we will find that the hydronium ion is concentration is 4 times 10⁻8. This is the hydrogen ion concentration or hydronium ion concentration. And if it is the hydrogen ion concentration, what about the hydroxyl ion concentration? Well, hydroxyl ion and hydrogen ion concentration is equal. So if one is higher, the one will be lower to make the balance, right? So we can find from the same relation from here, and hydroxyl ion concentration. From there, we put the values. We find the Kw, use the Kw value for this year, and then hydroxyl ion is 6.2510. Question number 3. This is a little bit interesting. That 40 milliliter of 0.2 molar HCl reacts with 20 milliliter of 0.1 molar sodium hydroxide solution. Calculate the pH of the resulting solution. That means the problem is saying that if these two things react, there will be a resulting solution. Of course, there will be a resulting solution, right? Something new is being produced. HCl and sodium hydroxide reacting. First of all, we have to write the equation to know what is going on there. So HCl and sodium hydroxide reacting, producing sodium chloride and water. Interesting thing, right? From strong acid to strong base, we produce the salt that we eat. And this sodium chloride is being produced. Okay. The question is, the resulting solution, it is supposed to be neutral because it is coming from a strong acid and a strong base, and this is a salt, so it's supposed to be neutral. There is no acid or base in this solution anymore. But there is a trick here. It says 40 milliliter and it's 20 milliliter, and their concentration are not same as well. So their concentration and volume are not same. When they are reacting, there will be a resulting solution which is either acid or more into base. Whether, we have to find the, you understand already that we have to find the limiting reactant first. Which one is the limiting reactant out of this HCl? And so the resultant solution will be the excess, will be influenced by the excess reagent or reactant. HCl, we took 2.2 molar 40 milliliters. The number of moles is times N equals C into V. N equals C into V, right? N equals C into V, so that N equals C into V. So from there we find the number of moles of acid, right? Number of moles of the acid, and then same way we find the number of moles of base, that is sodium hydroxide. And this is a 1:1 reaction. The ionic reaction is shown here. It's no problem. You can show this way. 1:1 reaction is, this is a 1:1 reaction. So if 1 mole of sodium hydroxide, 1 mole of HCl will be required to neutralize that sodium hydroxide, or vice versa. Since there are 2 moles of sodium hydroxide and 8 moles of HCl, this is for a very simple example, but things can be not be simple all the time, right? So since 1:1 reaction, I will need the 2 moles of HCl will be gone or will be used up. The rest 6 molar of HCl, 6 moles, 6 times 10 negative third moles of HCl will still be in the solution. And the solution is made of sodium chloride and water. Water is already neutral, we know. Sodium chloride is also neutral because it's a salt. It's not so acid or base, and it's a neutral salt because it is coming from a strong acid and a strong base. So it is also neutral. Now the solution, let's say this is in a beaker. All this thing in a beaker. Sodium hydroxide finished already, but the 6 moles times 10 negative third moles of HCl is still there. 6 times 10 negative third mole of HCl is still in the solution. So the solution is being influenced by this number of moles of HCl. All right. And another thing, since pH is negative logarithm of hydrogen ion concentration, not the number of moles, yeah? Concentration. Sometimes the student will just put the number of moles here. It will be a big mistake and wrong. It will not get number. It is third bracket means is the concentration. Although it's moles, it is mole, right? But here, when we must put in a concentration. And now, interestingly, the concentration has been changed. It is not 40 milliliter anymore. 40 milliliter of HCl we used, but in that 40 milliliter, we used another 20 milliliter of sodium hydroxide. So 40 plus 20 is 60 now. Is 60 now. So the concentration will be changed, and concentration changed to 0.1 mole per liter. Which one, plugging that value in here is giving us the pH is 1 of the solution. Weak acid and weak base. Weak acid and weak bases. We have used this acetic acid or ethanoic acid in many cases. In many examples, we have used this. And we have seen that we told that this is a weak acid, right? Because they do not dissociate properly, or they do not dissociate fully. Dissociate fully means just like ACl, 100% all of it goes to hydrogen ion and chloride ion. But for this case, this CH3COOH, it goes to dissociate in this way, CH3COO and hydronium ion. For simplicity, we can just put hydrogen ion for our convenience of understanding, or so that we know in this way. But most of the CH3COOH is still in the water CH3COOH in the solution, most of it. So that is why, since it does not dissociate fully, it is actually a weak acid. Okay, and by losing that hydrogen ion, it is not an acid anymore. Right, it is not an acid anymore because it has lost the hydrogen ion already. It has lost the hydrogen ion already. It is not an acid. So what is it now? It is able to receive a hydrogen ion later on. If somebody very strong, powerful comes and say that, okay, I have one extra hydrogen, do you want to take? It will say, because it is a negative charge. It is carrying a negative charge all around, and it is quite troublesome for it. So it will always take the hydrogen and become neutral. If there is a hydrogen ion comes here, it will become neutral. So it can accept. Whether it will take is a different question, but the thing is, it can accept one hydrogen ion later on, and that qualifies it to be a base. And that is why when acid or base, it dissociate, it produces a conjugate base. For acid, it produces conjugate base. For base, it produces a conjugate acid, because I think we talked it better, previously, because just to refresh your memories, water, H2O, since it took this hydrogen from here, it becomes H3O positive, and that is why it is able to deliver or give this hydrogen ion, one hydrogen ion, to someone who needs it. And it becomes, by delivering this hydrogen ion, it becomes H2O, which is much better for it to be stable, safe, and then no need to disturb anyone, no need to be disturbed by anyone. So this is that way it can be. So that is why it makes it a conjugate base. Okay, so all weak acid produces a conjugate base, and all weak base produces a conjugate acid. Same goes for this base as well. So ammonia is a weak acid, weak base, and then it does not dissociate or give the hydrogen fully, so that does not take the hydrogen ion a lot. A small percentage of it only takes it. So it becomes, by taking a hydrogen ion into its molecule, it becomes a conjugate base, because NH4 now, right? So positive charge. Positive charge means it is carrying a positive, an extra burden on it all over. Nobody likes it. You will also not like it. I will also not like it. I will just try to release that extra charge on me. And that is why it makes him. And how does it get release of that positive ion or negative ion? Is by releasing one hydrogen atom. If it releases one hydrogen atom, it can come back to this neutral, much stable compound, right? So that is why it is a potential conjugate base, potential acid actually, because it can produce, or it can donate one hydrogen ion to the solution. Acidity constant. Same like at equilibrium constant. For acid, we just denote this thing with Ka. So it means, the Ka means this is an acidity constant. And this acidity constant is only for weak acid. Or Kb, basicity constant, is only for weak base. All right. So same way, the constant, at equilibrium, the constant is formed by the same way. CH3, the product concentration by the reactant concentration. Okay, and then we find this Ka to measure the acidity constant. The higher the Ka value, of course, the stronger the acid. But we also understand looking at this reaction, equation, that why the Ka value will go high. If this numerator is higher values, right? If let's say CH3COO and H3O plus are higher value, like millions, it is 1 times 10 power 10, right? It's more than billion actually. So if it is the higher the value, I should not put any value here, otherwise you'll be confused. Okay, so if these two values are high up, like lot of values, how can I say that? A big value, it has a very big value, then the Ka value will also go up. If it is not, the Ka value is also going down. And how do I get the big value for this, the CH3COO and H3O plus? The more it dissociate, the more higher the value we get, right? The more acid dissociate, the higher the CH3COO or anything is there, we will get. And to get it more dissociation, we have to have a strong acid. Only strong acid will get more dissociated. Weak acid will not. And that since weak acid does not dissociate more, the Ka value is usually low. And lower the Ka value, the low weakest, the lower the acid or weakest the acid. Okay, so the Ka value goes down, Ka value goes down, the acid strength is also going down. Acid strength, hydrochloric acid is power 7th, is very big, Okay, and then phosphoric acid, and then let's say which one, hydrocyanic acid. All right, hydrocyanic acid we have. So this hydrocyanic acid has a pH or Ka value is 4.9 times 10 negative 4 tenth, which is a very small compared to, let's say, acetic acid, 10/5. It is 10/5, it is 10/10th. So it is much lower, low or weaker acid. There is another relation that we can show, just like pH and hydrogen ion concentration, H, concentration of hydrogen, and pH, right? pH is negative log of this hydrogen ion concentration. Negative log of hydrogen ion concentration is equal to pH. Same thing goes with the pKa value. So pKa is equal to negative log of Ka value. Now the table has turned. This is just another way of expressing, but nothing has changed. Only the expression and the values change. The higher the pKa value, right? The higher the pKa value, the weaker the acid is. The lower the pKa value, the stronger the acid is. So it's just another way of expressing. There are some, of course, usefulness of it, but we are not discussing here. It's usually for buffer, it is very important. All right, for example 4, it says that calculate the pH and percentage hydrolysis of a 0.5 molar ethanoic acid solution, given that the Ka for ethanoic acid is 1.75 times 10 negative 5. All right, pH and percentage hydrolysis, there are two things. We know the pH, right? We can find the pH and percentage hydrolysis. What does it mean? What does it mean? Percentage hydrolysis means how many percentage of the acid has been dissociated at that specific time or particular way. Now the question is asking the 0.5 molar ethanoic acid solution we have, and the Ka of the ethanoic acid is given, right? 1.8 or 1.75 times 10 negative fifth molar. We have to find the pH of the solution. So pH, to find the pH, first of all, pH is negative log of hydrogen ion concentration. Negative log of negative log of hydrogen ion concentration, or H3O plus, right? Same thing. How do we find the hydrogen ion concentration? We have to find the Ka value, because from the Ka we can find that it is actually hydrogen ion concentration, or which one is easier for you? It is not easy for me to write hydronium ion. Okay. And CH3COO. And here it is acetic acid, CH3, or ethanoic acid, COOH. Right? So we can see that, okay, somehow if we know how much is this hydronium ion, we can find the pH of the solution. Right? So we got a clue. The Ka is already given. The Ka is already given in this reaction or solution. Now we know that whatever temperature or whatever dissociation happens between them, hydroxyl ion concentration, hydronium ion concentration, and CH3CO concentration should be the same. Is actually given here. So it is actually the same thing, or equal, not same thing, but equal. The concentration or the value for both of them are equal, right? The Ka value is given. These two values are equal. So since we need this, not this, to calculate the pH, we are not considering this, but we just multiply or power 2 of the hydronium ion. And from here, we started with 0.5 molar of acetic acid, and since it is a weak acid, it does not dissociate fully, or very small amount. Is such a small amount of this acid is dissociated that we can consider basically that it is nothing has been dissociated. A 0.5 still 0.5 molar. Okay, still it is 0.5 molar we can consider. So that is why 0.5 molar we are putting here. This is the value we are putting. And it came from the question is saying that is 0.5 molar of ethanoic acid. We are considering that it is such a small value, it does not dissociate. But we need to do some little check, and we are not going to learn it here. Maybe in the degree, if we want to take, we will learn. Okay, so we just put this value in, and then from there we find that hydroxyl ion, hydronium ion solution, concentration. And taking care of these powered values, the hydronium ion concentration is 2.96 times 10 power negative third, and we can find the pH very easily. Negative log of these values. pH is 2.53. Percent hydrolysis of weak acid. Now, yeah, the percent hydrolysis. How do I know the percent hydrolysis of the weak acid? We started with, we knew it is 0.5 molar of the acid that we started with. And then here we see that hydronium ion concentration is 2.96 times 10 negative third, right? So since we already considered that this thing and hydronium ion is the same, equal amount, they are both equal amount. That's why we consider powered, right? So hydronium ion concentration is this one. So this is the CH3COOH concentration as well. COO negative concentration as well, right? So this much amount of acid has been dissociated, we can consider. This much acid has been dissociated out of this much and percentage. So this is 0.5 or 0.6% acid. This is only 0.6% of acid is dissociated. All right. So this our assumption that we considered here, it's 0.5 is correct. If it is more than 5%, if it is more than 5%, right, dissociation, then we have to consider -x and something that we will learn later, not here. Okay, so methanoic acid, example 5. Methanoic acid, which is commonly known as the formic acid and active ingredient in bee sting and ant stings. So it was found that a solution of methanoic acid, HCOOH, a concentration of 0.1 mole per liter or 1 molar, 0.1 molar, had a pH of 2.4. Calculate the acidity constant of methanoic acid. The concentration, it was found that the solution of methanoic acid is a concentration of 0.1 molar had a pH of 2.4. We know the concentration of the solution of the acid, and we know the pH of that. So from the pH, we can find the hydronium ion concentration or hydrogen ion concentration. H3O plus, right? Hydronium ion concentration. How? It is the anti-log of pH 2.4, 10 power negative 2.4. So from there, we'll find the hydronium ion concentration. And since we know that hydronium ion concentration already, right, that is actually this is the hydronium ion H3O plus, same thing that you might know. So this is H3O plus, and this is the value we just found from that equation. We just plug in the value and we find it. Right? We started with 0.1 molar solution. It is a weak acid. Methanoic acid is a weak acid as well, and it does not dissociate appreciably much, so we can just consider as it is. So the Ka value was found from here. Now we are going to the buffer solution. All right. So buffers. So is there any question anyone else has? Brian says that for the alternative method, why it is 0.03 molar? I think it was quite far, yeah? Oh, yeah. So 0.03. What is the problem? Oh, it's 0.3 molar, yeah? Point three should be 0.3. It was a typing mistake. It is not. It's 0.6. It should be. So most probably, let me check which one is correct. Negative log of 0.6. No, it is 0. It is correct actually. It is 0.03. 0.03. So the question should be changed. Let me check this. this question as well. 10 power negative 14th over it should be 0.03. Thank you for the. It should be 0.03, yeah. 0.03. 0.03 is not 0.3. Okay. Okay, so is there any other question anybody has? Thank you, Brian, for this. No. Right, so in this case, I'm going to take a short break, 5 minutes maybe, and then I'll come back and talk about the rest of it. Okay. All right, I'm back. So one question just came in from Brian, sir, for the answer for 1C and the alternative method. Are the answers supposed to be the same? Yeah, for alternative question should be the same answer, right? Because the alternative method actually, I mean, should be the same thing. Same thing, only the alternative method. Yeah. So please be informed that this is not point. This is not 0.3. It should be 0.03. It is 0.03 actually. 0.03 times 2. Okay, it is. All right. $12.78 for 1C. Let me check. So 1.66 10 power negative 3, isn't it? 14 power negative 14 over 0.06. Oh, 1.67 times 10 negative 13 we are getting, and here we are getting yes, I am getting 12.77 as well. So for this case, I am getting 12.78. And for this case, it's 1.21. Yeah, this is true. 1.21. Yeah, the problem is here. It is not 13.78. It should be 12.78. Thank you for making it. I mean, bringing it to my note. So I will change it accordingly later on. All right. So now go to the buffer. So buffer, oh, my camera, where's my camera? Right. Buffer, I'm sure that you have heard this term before, not for the chemistry or chemical purposes, but for other political, socio-political things that you have heard of it. Nowadays, we call it, make it a buffer, buffer place or buffer situation, right? Or buffer zone. We can we call these things. So that is chemical term has been used and integrated to some socio-economic, socio-cultural purposes. But buffer, the meaning is that it can absorb a lot of shock. Shock means for this case, for our chemical purposes, that when there is a buffer solution, it can absorb a little bit of excess acid or excess base that we use in the solution. Okay, like you put a little, I have to produce a solution, right? Because there are a lot of things that we need to keep or need to preserve in a solution for quite some time, and then changes the solution, the acidity will cause the substance to damage. For example, some of us, we use that contact lens, right? We have to keep it in a solution. That solution is a buffer type of solution, all right? So, and more importantly, our blood is itself a buffer, right? So what is the buffer solution? That if we add or change a little bit of additional thing to that, whether it can be acid, it can be base, or it can be anything, salt or anything, it will not change that the pH of the solution. Like we started the pH of the solution 7 or 8, it is still around 7. So how do we make it? For that, important thing is buffer solution cannot be made with strong acid, strong base. All right, strong acid, STR. Okay, strong acid, STRNG, strong base. Strong acid, strong base cannot produce buffer. First thing, if there is a strong acid, strong base, they are excluded. First thing, they are not qualified. The first step, they are gone. It must be a weak acid and the salt of its conjugate base. Now remember what is the conjugate base. Just now we were talking, right? Or in another way, it can be a weak base. Not necessarily it has to be acid. It can be a weak base and the conjugate acid of that base. Salt, of course, salt of that conjugate acid of the base. So buffer, let's say, I mean, our easy example is the acetic acid or ethanoic acid. And ethanoic acid, when it dissociates, it produces, this is the conjugate base, right? We talk about it, the conjugate base of it. So if we have in the solution acetic acid and a salt that is made from this conjugate base, a salt means what? Salt means the metal is added, all right? Let's say sodium acetate or potassium acetate or barium acetate or something like that. Lithium acetate, also lithium acetate cannot be used. So sodium, potassium, let's say acetate are in the solution. In a solution, in a beaker, let's say this is a beaker, right? So I put acetic acid, this one, CH3COOH. I should write it here, CH3COOH. And I also add sodium acetate, CH3COON, Na. Both together I put in this beaker. What will happen is automatically it will produce a buffer solution. Automatically means they will produce a buffer solution, but of course we do not know, if we cannot control or it is not desired. How to put it? It is not. It will produce a buffer, but to produce a buffer with a desired pH, like I want a buffer that will have a pH of 5 or 6 or 4 or 11 or 12, I should be using exact amount, exact concentration of this acid or salt of that conjugate base of that acid, and accurate volume as well. So that's what I'm saying, that if we just throw in anyway, it will produce a buffer, but we do not know what is the pH of that. But the thing is, they will produce a buffer solution. All right. So when when we add, how does it produce a buffer solution? When we add, let's say this is a buffer, sodium bicarbonate is there, and acetic acid is there. So when we add a little bit of acid in the solution, right? Not a lot. You cannot just put a lot of acid, then you can expect. I mean, that the solution will be still same pH. No, it doesn't work like that. A little bit of acid or base should be okay. So if I add a little bit of acid, what will happen is the reaction will go to the right. All right, isn't it? The reaction is going to the right if I add a little bit of acid. Is it? If we add a little bit of acid, the thing is the reaction is going to the left because acid is giving the hydrogen ion, right? Hydrogen ion. This is a little bit confusing, so you should pay attention. Acid means hydrogen or hydronium ion. So far we have called it hydronium ion. I also said that for simplicity we call it hydrogen ion. If I add hydrogen here, what will happen? Hydrogen is going and attaching there, right? Like this. So it is, the reaction is going that way. I mean, it's producing acetic acid, that means going backward. If I add hydroxyl ion, in the solution, what is happening is this one is going to react with hydroxyl ion and then producing water, right? And that means there is a void here. There is a emptiness here. So the reaction, to fill up this emptiness, more acid is being dissociated to produce this hydronium ion. So the reaction is going to right side, moving towards right. So that is how the buffer solution works. It is not that difficult thing, but this is it. We will be looking at the buffer now. So the buffer solution, carbon dioxide actually, in our, when we exhale in carbon dioxide, and when we inhale oxygen. So it produces bicarbonate ion. This is the bicarbonate ion that is produces by this carbon dioxide. When we in our body, when there is a carbon dioxide, the bicarbonate ion is being produced, and that bicarbonate ion, carbon dioxide and water, it produces this is a buffer solution. All right. So if I remove this, carbon dioxide when I exhale too much, right? I'm exhaling. So what is happening is I am expelling all the carbon dioxide from my lung. So there is no carbon dioxide in that. So what will happen? The reaction goes backward. That means left. The reaction rush backward because there is a void here. Carbon dioxide reduces, so it has to produce more. So the bicarbonate ion that our body has, it will rush towards left, and that is why the hydrogen ion will also reduce because going left, and the pH of our body will reduce. Vice versa is if I have more carbon dioxide in our body, if I did not breathe for some time, the carbon dioxide built up, and then more bicarbonate ion will be produced. The reaction will go forward. The reaction will go forward, and then hydrogen ion will increase. The pH of the solution, the pH of the solution will reduce in that case, right? The pH of the solution will reduce in that case because hydrogen ion is increasing, so pH is reducing. Okay, and then if carbon dioxide is removed from the system, the hydrogen ion reducing, so pH increases. Did I say the inverse way? Okay, so if I reduce the carbon dioxide, the pH will increase the solution. And sometimes if we exhale too much, like do some exercise and then we exert too much, we'll feel little bit nauseated, and then maybe you feel dizzy because the balance is not a bit distorted. It is not very dangerous, but if it occurs every time that you do and it is dangerous, then so you should go and take to the doctor. So, and if the carbon dioxide is removed too much, with that, if we breathe too heavily, so some oxygen is also going out, and then our body, the pH is being increased to some extent, and that's so many things. Anyway, okay, so this is the thing, and our body, and why bicarbonate ion is important for our blood system, because it is same like this. Bicarbonate is the same buffer system it produces in our sea. The buffer system, it produces the bicarbonate ion system, and this is the bicarbonate, and this is, we can call that this bicarbonate system, buffer system, is one of the, or maybe the key for the life on Earth, because of this buffer system. Okay, so this is our buffer system, blood buffer that is happening, and if our blood has more than 7.5 or 7.45 to be precise, pH, all right, our blood is called alkalosis. If it is 7.35, it's called acidosis, and it is dangerous. If more than 7.8, we die. If less than 7, we die as well. So our blood buffer must be around 7.35 to 7.45 to function our body well, perfectly function our body. It should be 7.45 or 7.35. So we understand that we are walking on a thin line, right? If we add drink or take too much of acidic or basic thing, I think it's not a good idea, but don't stop taking the lemon or apple cider. Is good for your health, not too much. Of course, there is some standard volume that you should take. Okay. What is that? So this is our summary for this, and sulfuric acid production. Just for information, sulfuric acid is being, it is one of the second most important or second most produced chemical in the world, after, I forgot actually where, after what, but this is written second most produced chemical, because this is such important thing or reagent that we need for metallurgy, petroleum refining, fertilizer, other chemical manufacturing, many things we need sulfuric acid. So this sulfuric acid, how does it need to be produced? And many countries that produce sulfuric acid. So how do you put it? We start from the molten sulfur. Sulfuric acid is H2SO4. Yeah, I think I should tell you first that H2SO4 is the sulfuric acid. So there is two parts of hydrogen, 1 part of sulfur, and another 4 parts of oxygen in the sulfuric acid molecule. How do you start it? We have oxygen and hydrogen from the air, we can find it, but we start from the molten sulfur. The sulfur that we find from the mine, from the cave or mining, we take it out and then melt it, and the molten sulfur is sprinkled from the top. It's just a schematic diagram here. It's not actual, but I hope that you will get an idea of it. And for those who will take chemical engineering, you will have in the 3rd year, 4th year, you will have detailed or drawing and designing and all those things for production of different type of molecules product. Okay, so the molten sulfur is melt first. It is melt at high temperature, and then it is sprinkled from the top. And in another chamber, the air is coming in. Air is pushed at a high force. So what happens is the molten sulfur, when it comes down from here, it mixes with the air. Mixes with the air, and sulfur dioxide is produced. So SO2 is being produced. Sulfur. I should write it here. Right? Sulfur dioxide means here is sulfur dioxide, SO2. Sulfur dioxide is produced. This sulfur dioxide is still not, it's far from SO4, right? So what we do is we want to make it, we want to put one more oxygen to this sulfur dioxide molecule. Sulfur dioxide is quite already is stable actually, but we want to thrash in another oxygen there, another 2 oxygen in fact, atoms to there. So what do we do it? There's a reactor. We channel this sulfur dioxide to a reactor. In that reactor, there are many catalysts and there are many layers of catalyst. Yeah. So the air, again, oxygen, air is thrashed in because we need oxygen, more oxygen to be bind with the sulfur dioxide molecule. So air is pushed into that surface, and then this sulfur dioxide, the hot, still very hot sulfur dioxide gas, it goes through this bed because these are perforated. Perforated means there are many holes, right? There are many holes in this rack. So, and the catalyst is there. So through the catalyst, through this rack, it goes through there. And only then sulfur trioxide is being produced. Okay, sulfur trioxide is being produced only there. So this sulfur trioxide, once it is produced, SO3, just to put another oxygen is so hard. So SO3 is being produced here. This SO3, you cannot, we cannot put another SO4. We cannot make SO4. It's almost not impossible, but very hard, and it is not economically feasible. So what we do is sulfur trioxide is being pushed here, and then concentrated sulfuric acid is channeled from here. Still it is hot, right? It's going from bottom and it is coming from top. Why it's coming from top and bottom? This way, so they can hit each other at a maximum force. Right, we want them to hit each other maximum force, so the reaction occurs actually. So maximum force, and then there is a they bind each other well. All right, so since sulfur trioxide and H2SO4, right, H2SO4, it is coming down. Is concentrated sulfuric acid, there is no water, and it is reacting with SO3. So what will happen? What happens is H2S2O7. S2O7. This is called oleum. This is oleum. This oleum is produced and then it is removed from this duct or from this valve, and this oleum is later on, if we need to produce sulfuric acid, we just need to dilute it. We just need to dilute this oleum to produce sulfuric acid according to our need. All right, so this is actually the production. This is a very simple way of describing that. This is much more way. So yeah, so here it is that molten sulfur, and it reacts with this natural from natural gas or crude oil. We can find the sulfur, or from the mining. we can also find the sulfur, and then it is sulfur dioxide being produced. Sulfur dioxide and oxygen produces sulfur trioxide, and it's exothermic reaction. And then it produces a lot of heat, right? And we have to remove that heat as well to produce more sulfur trioxide because of La Chatelier's principle. And yeah, that's it. So conflict. At first, there are two case scenario. If let's say consider a chemical engineer, he has some problem in front of him and then or her, and he has to find out the solution for this. That to increase the rate, if I increase the temperature, of course it will not increase because this is a exothermic reaction. So we have to decrease the temperature. Increase the pressure. If I increase the pressure, yes, because it will move to the lower number of particle here. 2 plus 1, 3. Here's 1, 4, 2. So I can, if I increase the pressure, it will. But in this vessel, this converter, right? This converter is how big do you, can you imagine? This is maybe few thousand gallons. Right, few thousand, very big one, and pressurizing it to some extent is very expensive method. So better use the catalyst. All right, better use the catalyst. And the conflict will be that at first a fast rate occurs at high temperature, but the best equilibrium yield occurs at lower temperature. Right, equilibrium occurs. Equilibrium yield will be at low temperature, but for rate production will be fast at higher temperature. So what can I do? We have to do some trade-off with some time. That if we use 400 to 450 degrees centigrade, it's not very high, but it's not very low as well. And vanadium pentoxide. So this is a mixed method, blended method. I'm using temperature and catalyst both, so that at high temperature, I don't need to use it. And also this, we can reduce the temperature from that exothermic reaction and use the catalyst, so that both is a simultaneous process. It will produce the most hydrogen sulfuric acid, sulfur trioxide actually. And if water is added to sulfur trioxide, the reaction is so exothermic that hydrogen sulfuric acid will be formed, but it will all go out in vapor. And then it is fogging, and then it goes to bring it down to liquid. It is a huge cost, because you have to wait, or you have to remove the heat from that vapor to get it to the liquid form of sulfuric acid. So not to do that, just channel the sulfuric acid and produce the oleum, right? And that oleum, we dilute it with water to produce sulfuric acid later on, according to how many percentage. You need 40%, you need 60%, you need 20%, 30%. You make it accordingly that way. All right, so this is it actually. The sulfuric acid production was just for your information, and I hope that it helped. So is there anybody has any question here today? Any question? All right, so if no question, then I think I'll stop here today, and I'll see you on Thursday for the lab. And I hope that you have seen my announcement that your test 1 will be on week 11, that is 2 weeks from now. And you have already seen what chapter will be included there. So yeah, I'll see you on Thursday in the lab. And also those who are not coming, I'll see you through the MS Teams. All right. So thank you. Yeah, thank you. Thank you. Bye bye. Take care. Have a nice rest of the day. Yeah.